Hi everyone, welcome back to these Python tutorials where we are focusing primarily on image processing and image analysis. In the last few videos, we looked at performing semantic image segmentation and image classification. Like when it comes to semantic image segmentation, we are referring to classifying each pixel in an image to one or more classes. And when it comes to image classification, we are classifying the entire image to a class. Now, when it comes to classification, image classification, for example, an image can be part of, or let's say we classify an image into sunset, another image as a landscape, another image as a dog park, or we can have multiple classes. In those situations, we used a metric called accuracy. Obviously, I'm pretty sure all of you are familiar with accuracy, which is basically what is the original class and what is the class that we are predicting it as. And we look at, for example, 100 of these images and we say, okay, 99 of them are correctly classified, so our accuracy is 99%. Now, that type of accuracy is not a great metric for semantic segmentation, because in semantic segmentation, you may actually have an image, something that looks like this, right? I mean, if you look at this image, bulk of these pixels belong to two primary classes, one blue and the other red, right? So, and if you only look at the yellow and the green classes, these are minority classes. We don't have much of this. So when you fit this to a random forest, the random forest machine learning algorithm can be a bit biased towards these majority classes. And it's not just random forest. It can be deep learning or any other machine learning problem. If you're supplying a lot of data for one class compared to the other, the model may be a bit more biased towards the majority class. So if you only look at accuracy, let's say you are actually getting great accuracy from this blue and red, and maybe even from the yellow phase. Maybe the yellow phase is easy to segment because you have these pixels are too bright, right? So in those situations, and what if the green one is a bit difficult to segment? We don't have a lot of labels for the green ones, right? This is what I'm referring to as a class imbalance in a way. And in one of the upcoming videos, we will look at how to address the imbalance problem. But for now, let's focus on what is the right metric to evaluate how good the model is performing for each of these different classes. So accuracy itself on this data set can be 95%. If you just look at the segmented result here, yeah? Original label, segmented result. Original label, segmented result. It looks like this blue area right there, we're doing great job. I think we are mixing colors here. I mean, the segmented image shows up in different colors, but if you just look at these areas, most of these areas are easy. If you only look at this greenish area, you see there's a lot of gaps right here, a lot of gaps right here, missing pixels, a lot of misclassifications right there. Okay, now what is the right metric? And the right metric is something called IoU, which is intersection over union. And as the name suggests, by the way, this is also referred to as Jaccard index. Okay, as the name suggests, this is the area of overlap between the predicted and the ground truth, right? What is intersection? It's the overlap between my predicted and the ground truth, right? What is this overlapped area? How many of those divided by the total number or the union between the predicted and the ground truth divided by, so this area, in fact, I have a graphic. So it's the intersection area divided by this entire union area. Okay, so this is what intersection over union is. Now, why is this going to be helpful? Right? Why is this any better than accuracy? If you want to know that, let's just simulate 4 pixels, right? 4 pixels in ground truth, 4 pixels in prediction. None of them are overlapping, meaning my prediction is not that accurate. So if you look at this, my IoU equals to 0 because my intersection is 0 right there. Okay. Now let's actually get 1 pixel overlapped here, meaning if you my intersection here is 1 pixel and the union here is just add all of these, right? So 1, 2, 3, 4, 5, 6, 7. So 1/7 is IoU value in this case. Now, the extreme case, which we all aim to get to, is where you have an absolute overlap between these two, in which case your IoU should be equal to 1 because your intersection is same as your union. So this is where you're getting a value of 1. For IoU. So as you can clearly see, this makes a much better parameter to assess the quality of our segmentation compared to accuracy. So again, for multi-class segmentation, this is just one single class we are talking about, or two classes, right? A and B. But if we have multi-class, the mean IoU of this image is calculated by calculating each IoU. So now in the next 10 to 15 minutes, let's actually look at the example we already looked at as part of our semantic segmentation. And now let's print out or see a couple of ways to calculate this intersection over union. So let's jump into our Spider IDE, which is my preferred IDE because I can quickly look at variables while I'm working with data. And we'll see that in a minute, in a moment. And here is our Spider IDE. And again, just to reiterate, the reason I like this is as soon as I execute a line, I can look at the variable explorer to see if the variables are right or wrong. Or am I doing the right things without including a lot of print statements. But if you work with Colab or other notebooks, that's also fine. It's up to your comfort. Okay, getting back, first to make sure, am I in the right directory, present working directory? Go ahead and yes, I am in my code directory where I have all my code. So this is good. This is a good idea to check. Otherwise, the image paths, for example, that you're giving, or any path to referencing to a local file will be wrong if you're not in the right directory. Again, these are the basics, but we all have done these type of mistakes, so it does make sense to check that occasionally. Now, a good trick to make sure that you are in the right directory is by default Spider moves the your present working directory to wherever this file is as soon as you run this entire file. So you just make some semantic mistake here and run this, and it'll throw some error right away. But then because it's executing, it changed my present working directory to this specific directory. Again, little tricks that I kind of learned to do while working with Spider. Okay, now that I know I'm in the right directory, let's go ahead and run the code. Again, I have done this. We have gone through this code in a meticulous way, in the previous tutorial. So let's go through this at a faster pace just to make sure we understand the application and then focus on the intersection over union part. Okay, starting with the libraries. These are all the same libraries we have done before: NumPy to handle or NumPy arrays, OpenCV to open images into Python, pandas to handle data into almost like a data frame, or Excel type of data handling. Datetime, I included this to see how, if we want to see what the execution time is, we can keep track of that. And from scikit-learn.metrics, we are going to report certain metrics there. You can import pickle if you want to save the trained model and then reuse it. And obviously pyplot to have a quick look at images, and OS to walk through your local directories. Now, let's start by reading the training images and extracting the features. First, I am going to start an empty data frame, and I'm going to read images from this directory, train_images. And again, please watch my previous tutorial on semantic segmentation. Went through each of these lines in a careful way. And first of all, let's go ahead and run these lines so you can see that, okay, I am in the right directory and I have about these many images for training. And each image is, you'll see that once we start reading, but each image is 768 by 1024, or I mean 1K by 1K. I think they are 1K by 1K images. And we are going to read each image from this path, right? Each image. And if the image is, number of channels in the image is 3, then we're going to convert that into grayscale. Otherwise, we are just going to work with grayscale images. I mean, in this case, these are all grayscale images anyway. Now, the next step is add the pixel values as one of the features itself, because all we are trying to do is read or train images and extract features and capture all the features into a data frame, and also read the masks, the corresponding masks, and train a random forest on these images and features and masks as the ground truth. And once you train it, now the next step is to evaluate how good the trained model is. That's where the intersection over union comes into the picture. So we are going through all of these steps to make sure we get there. And I'll quickly explain what's happening here. So first of all, one of the features I'm going to add to our data frame is pixel value itself. because that's a great feature, right? If my pixel is bright, that tells me something. If my pixel value is very low, that tells me something. So that's feature number one. Then I'm going to generate a whole bunch of features by changing the some of the parameters as part of my Gabor kernel. Again, watch my video on this, what Gabor is. Gabor is just a convolution where we can define the convolution by defining the kernel size, by changing the sigma, theta. So it's basically an easy way of creating many digital filters just by changing a few parameters. Okay, so we are going to do that, and then we're going to extract certain additional features like edges and what else are we trying to do? Smoothing, Gaussian smoothing, and these are all my filters that I'm going to use to fit my random forest algorithm. So first thing first, let's go ahead and extract all of these. So let's run these lines of code up to the point where we read the mask. And this may take a little bit because these are large images and we are extracting features from these images. So let's go ahead and look at this. As you can see on the screen, we are generating a whole bunch of Gabors, like about 31, 32 Gabor filters. And we are adding these extra filters on top of that. Now, which ones are good? Are all these Gabor filters good? Again, please keep watching this channel because I'm going to make a video pretty soon on the topic of feature selection. Okay, we select all of these features, but just let's test this on a smaller data set and identify the ones that really matter, and then train our bigger data set using these subset of features, because we know these are the ones that actually make sense. Okay, please watch that pretty soon. But we are done with our image data set. So if you look at our image data set up here, in the it's 42 columns, and as you can see, the column values are pixel value, the columns are pixel values, image name, Gabor 1, Gabor 2, and all of these that we just added. And just before, and by the way, we are unwrapping this. We are actually reshaping this. So our features are not just 1024 by 996. It's in fact 1024 multiplied by 996. I'm capturing everything into a single column by reshaping them. So we have, on the whole, how many ever? This I think is, if I am correct, 10,199,040 pixels altogether in all of the images combined, and 42 columns. So this is tremendous amount of data. Let's capture our masks in the same way, but for masks, we are not doing any feature extraction. Obviously, our mask is the ground truth. So all we are doing is read the mask as is and just create a data frame or add this to our data frame. So let's go ahead and do exactly the same. We're not adding it to the data frame yet, but we are capturing this as a separate data frame. So if you look at mask dataset, we have exactly same number of rows or pixels, except we only have two columns. One is for label value, right? What is the value? This is our ground truth, and the other one is just the mask name. Okay, so once we have that, let's combine these two into a single data set. These are two different data frames. We are combining them into a single data set at this step. So we are concatenating them both along axis equals to 1. Okay, so it actually acts as another axis. So if you look at data set up here, now we have same number of data points, except we have 44 columns instead of 42 because we added the two columns from mask to the data set, right? To our image data set. Again, if you are not familiar with pandas, we made a video on that. So just check for pandas tutorials in this playlist. So now bulk of our pixel values are zeros, and which is normally okay, but in our example, in our case, we are using partial labels for images. We are not using the full labels. Meaning, if I have an image, my mask doesn't have all the pixels labeled because it's very laborious to do that. So we only labeled few regions in each image that we thought were very important. Which means all the areas where we haven't labeled, they were all given a value of 0, and they should not be used as part of training here. And this step is applicable only if you have partial labels, right? Where the unlabeled regions are given a value of 0. So in this step, I'm dropping all the values, all the pixels, or all the rows where my label value is equal to 0. So I'm keeping only the ones where the values are not equal to 0. So my entire data set, now it should go from 10,199,000 down to 372,000, because these are the only pixels we labeled. Okay, I hope this makes sense. Again, go back to the original video where we spent a lot of time trying to understand every step here. Okay, now let's define our x and y so we can fit this to random forest. Again, my x is the entire data set, but we are going to drop the columns labeled image name, mask name, and label value, because these do not reflect the features. Okay, so we are going to drop that. And my y is our ground truth, which is basically the column labeled label value. And I'm converting that into a NumPy array. So at this point, now we have our x and y. I'm ready, almost ready actually. But my y values, they go from 1, 2, 3, right? So if you look at your y, the y values are going from 1, 2, 3, 4, because we dropped all zeros. But when you calculate intersection over union, or when you use some of the standard libraries in Python, and you would like to use them for multi-class problems, they assume that your classes start at 0, 1, 2, 3. So in order to minimize any confusion, I'm just re-encoding my labels as 0, 1, 2, 3 instead of 1, 2, 3, 4. That's it. I could have just taken this and subtracted 1, but this is best practice. Label encoder. Okay, so let's go ahead and do that. And by the way, this is exactly what you use if your labels are again, dog and a cat and a rat and a mouse, right? Rat and mouse are the same, but if your labels are text, you use label encoder to actually convert them into 0, 1, 2, 3 so your computer understands. These are the things you need to learn to get started with deep learning, which we'll start in a few upcoming videos from now. Okay, so now my y values, if you look at my y up here again, they are back to 0, 1, 2, 3, 4. Again, now let's go ahead and split our x and y into testing and training. So we are holding out some of these for validating or training, for testing our model, how good our model is performing. So we are breaking our xy values into x train, x test, y train, y test. Okay, so we have both x values and y values for training and testing. So far, so good. Now let's go ahead and fit this to random forest. Again, we are using the one from scikit-learn.ensemble, and we are going to use 50 trees, or number of estimators as 50, and we are defining a random state just so we get reproducible results every time we run this. So this is just creating an object called RF model. Now we need to run this model. We need to fit this model onto our training data, and you know what that is, X train and Y train. So let's go ahead and do the training. This will take a while, even though we only have 372,000 data points. Random forest in scikit-learn is not does not leverage GPU, for example, just like deep learning does. So this will be a bit slow depending on your resources. And once this is done, let's go ahead and talk about intersection over union. So let me go ahead and pause this video until this is done, which probably should be 30 more seconds. Okay, now that this is done, let's see how long it actually took for random forest. This is probably a minute or so. Yeah, about 1 minute and 3 seconds. I consider that to be a bit slow. And again, in the upcoming videos, let's see how boosting, for example, gradient boosting can help speed this up. Not just speed it up, but also improve the accuracy. Again, please subscribe to this channel so you get these tutorials delivered to you or notified to you. Now, let's go ahead and predict this. So we have our random forest model. So let's go ahead and predict. On our testing, prediction is pretty fast, and let's print out the accuracy. This is where our scikit-learn metrics will come into picture. So we are using metrics.accuracy score, and accuracy, like I mentioned earlier, all it's doing is looking at our ground truth, which we called y test, and the prediction, which we just made, we called it prediction RF, and then just literally looking at how many of these are correct and wrong. So let's predict, and let's see, we are doing pretty good, 95.25%. This is where the real question is. Now, does that actually mean I should be happy about the model that we just trained? Or am I not doing very good with the minority class compared to the majority class? So how do we find that out? So like we already mentioned, intersection over union is basically the intersection like between the two, like y test and predict, and divided by the total, right? The intersection of the two classes and divided by the average. And if you want to think about this in a different way, it's true positives, like how many of the positives did we get as positive, meaning how many pixels labeled as 1 did we get correctly guess them or predict them as 1. That's what true positive is, divided by true positive plus false positive plus false negative, right? These are the three different cases, divided by true positive, which is this, the ones that we got correct, and the ones that we got wrong, which means the number of pixels where we got of class 1 misclassified as class 2 or class 3 or class 4, right? Or number of pixels of class 3, 2, 3, or 4 that we misclassified as 1. So these are false positives and false negatives. Okay, so this is what IoU is. You can write your own code to do that, but there are two ways you can easily do this. One is called Jaccard score, and this is part of scikit-learn metrics. And this is basically intersection over union. Okay, so from scikit-learn metrics, I'm going to import Jaccard score, and I'm going to provide my y-test and prediction. Again, just like accuracy, I'm going to provide these two. And there are a few ways of doing average. I'll advise you to go ahead and look at the documentation. I'm using something called macro, which is looking at this entire data set. Okay, so let's go ahead and extract this Jaccard score and print it out. Okay, this is giving us the intersection over union for all of the classes put together combined. And this is giving us a value of 91.25%. That's not bad, actually. And average, when you put all of these together, getting 91.25 is pretty good. But again, how are my individual classes doing? And unfortunately, from this, you cannot get that information. This is why I recommend using the one from Keras. Again, if you plan on getting into deep learning, if you plan on learning deep learning, I definitely recommend you to install Keras. It's just pip install Keras, Keras, and you should have it. So from keras.metrics, I'm going to import something called MeanIoU. So let's go ahead and do that, MeanIoU. And here we have to provide number of classes as one of the inputs. So let's just put number of classes equals to 4 because we have 4 classes. And again, this is where it assumes that if I say number of classes as 4, it assumes that these are 0, 1, 2, 3. Okay, that's the reason why I did my label encoding. And now let's go ahead and do our intersection over union by using MeanIoU. Okay, now it created that object, and I need to update that object by providing the two inputs, right? Again, the two inputs are my ground truth and the prediction. So, which is, what we just calculated. So let's go ahead and update that. And as you see, the output of this, the reason why I like this is the output of this is a almost like a confusion matrix, where it gives you true, false, true, negatives, and all that stuff. Now you can look at this and extract the intersection over union for each of these classes. And the way you do that, again, I am going to extract right now this is in the form of a tensor. To work with these as a NumPy array, we have to convert this tensor into NumPy array, and it's basically np.array. Just follow this, and we are reshaping this. And if I print the values here, you should see exactly what we are talking about. You see here, it's basically in terms of a tensor. Right now, this is a NumPy array. Once it's NumPy array, I can extract this. All I need to do is divide this by the summation of these and these, right? I mean, this, and this. Remember, the true positive divided by true positive plus false negatives plus false positives. So that's exactly what we are doing here. And the next step is to print them out. So we get a good understanding of what worked well, what did not work well. You see, for class 1, it's 92.4% of IoU, which is good. For class 2, it's 76.5%. If you remember in my original image that I just showed you, the green phase where we don't have much of it, that's class 2. And class 1 is all the black pixels and or the background pixels. Class 3 is all the red pixels that you saw. We have a lot of it. And class 4 is this yellow pixels. We don't have a lot of it, but then it's easy to segment those. So class 2, we don't have much of it. On top of it, it's a bit difficult to segment. That's why our intersection over union is a bit low, and I'm okay with this. But we'll see if we can improve this anyhow, right? In any way. Maybe by balancing the data sets, or maybe by using boosting algorithms. So this is what we plan on doing in the next couple of tutorials. Again, please stay tuned. Do do not forget to subscribe to this channel, and thank you very much for watching this video.